Okay. Okay. So today we're going to talk about the adjoint representation, and I'm going to prove a formula called the Campbell identity. Okay. Let's just recall the definition of what a representation is. Is rho a map from a group G to GLV, where V is a vector space, and rho is a group homomorphism. Okay. And then we're going to define what a induced representation is. Note that this is different from the induced representation in group theory. So suppose you have rho, which is a representation of G, and then we have d rho at identity, which is from the Lie algebra to endomorphisms on V. So this is because, well, this is from the tangent space of this to the tangent space of this. So this is by definition. And here notice that GLV is open in in the set of n by n matrices. And so the tangent space is basically endomorphisms in V, which is the same as so that's the tangent space at identity of GLV. Yeah. Okay.
So do you remember how we what calculation we kind of did when so two questions. First of all, do you remember why GLV is open in
complement is closed?
Well, no, that's not exactly what we did. It's simpler. But okay, so we'll get back to first of all question is why is GLV open? And the second question is, do you remember roughly how the calculation went to show that the tangent space to invertible matrices is all the matrices?
No, I don't recall.
Okay. Okay, so GLV is open. Why? So remember, if you want to check if a matrix is invertible, how would you do this computation? You compute the determinant is non-zero. So suppose you have something where the determinant is non-zero, and you want to show, you want to show that some set is open, right? If you want to show that some set is open, it's equivalent to show that around every point there exists some smaller open set which fits in the whole set. Okay, and then I can take the union of all your. And so, how do we do this?
Well,
how do we check?
So you have the map determinant, which is from n by n matrices to R. And so GLV is equal to the pre-image of R take away 0, the multiplicative units in R. Sorry. And this is a continuous map.
Yeah.
So this is the pre-image of an open set under a continuous map, which is open.
Oh,
Yeah.
okay. Ah, okay. I see.
That's one way. Yeah. And then when you do the calculation for, what is the tangent space at the identity of GLV? What's the identity in GLV?
Is it the identity matrix?
Yes, it's the identity matrix. And so the question is, what are the tangents? The tangent space is kind of like all the directions in which I can go from the identity and still be invertible. Right? So I can go like infinitesimally small amounts and I'm still be invertible. So if you think about the identity matrix, right? Which entries can I change a little bit and I'll still be invertible? If I change an entry, well, sure, but what else? If I change any entry a sufficiently small amount, will the matrix stay invertible? Okay, 50-50, yes or no?
Yes.
Yes.
That is correct because
Which though? Or does it depend on
you can change any entry by a little bit and the matrix will still stay invertible. Why? Because the determinant is a continuous function, right? If I change the matrix a little bit, the determinant is not going to change by much.
Yeah, okay.
Okay. So this means because I can change any entry, right? Then all my possible derivatives, all my possible directions are I just change, any given matrix entry, but then that's just all the matrices. Okay, so I think that's a good thing to remember.
Thank you.
Sorry, you were going to say something.
I was going to say, like, you have an open set around it that's contained in GLV.
Yeah.
So if you, because it's open, so if you change it by a little bit, by in any direction, it's open in
the matrices.
Yeah, in the matrix. Yeah. So you can change it by any matrix that's sufficiently small.
Yes.
Right.
Good. Right.
Okay. We still haven't. Well, sorry. We need to recall another definition from last time. Which is what does it mean for something to be a representation of a Lie algebra? Because this is from. Sorry. Okay. A representation of a Lie algebra is a map. What letter should I use? I'm gonna use phi. From the Lie algebra to endomorphisms on V. Such that this phi is a group homomorphism, and phi respects the Lie bracket, which is phi of x y is equal to Lie bracket of phi x phi y. And so basically what we need to show is that this d row respects the Lie bracket. Okay. and we're going to come back to this. We're going to define what the adjoint representation is.
We want to show
And-
that the induced representation is like a good definition for the algebra.
No, we
or
want to show
someone-
that this actually is a representation of
the algebra. Okay.
this layout.
I see.
Yeah.
So given the representation of a Lie group, yeah, remember, what is a representation of a group? Like physically, why did we need this?
We could describe every group as something like semi.
Well, that's kind of, yeah, that's a bit useful. But physical sense, I need a physical
sense.
Remember?
Sorry, I wasn't here last lecture.
I mean, that's fine. I talked about this on the very first day, kind of.
My memory doesn't stretch that far.
So the idea was what? For example, I had, you could have like a discrete group of rotations by 120 degrees. That's a group with 3 elements.
Yeah.
Okay. But then, this group, on its own, the group, if you just look at the group structure, the group is just like I have a bunch of elements and I know how to multiply them together and get another element, right? So from a mathematical perspective, so from a physical perspective, I know that okay, if I have some group of rotations, then these rotations I should be able to like apply them to some vectors and rotate the vectors, or apply it to some like physical object, and then rotate that object. But then a group on its own doesn't have this information, because a group just tells you how do I multiply things within the group. Okay. So then I need a representation to tell me, how would this group act on these, on some other space. Yes. So this is really helping us like really get to describing symmetries of a system, right? Because now you have like a way, you have some group, and if you have a representation, then you know how this group like permutes things around in your vector space, and then you can then start seeing like, oh, is this a symmetry of the system?
To understand that, I think like what would a symmetry look like in a vector space?
Well, to say what a symmetry is, that's you don't have a symmetry of a vector space. You usually have a symmetry of some like physical system, in the sense of physical system. Usually you have like some additional information, like you have a Hamiltonian, or you have some equations of motion, and then the question is the does the representation of the group play nicely with these equations of motion in some sense, depending on what the problem is. But at least now we're able to formalize what it means for a symmetry to act, to have some kind of transformation that comes from something. And the other thing is, you now realize that you could have, for a single group, you could have different representations on the same vector space. So the same group, I can give it different representations on the same vector space. So it could act on this vector space in different ways depending on the representation, and that is often useful, which we would talk about at some point. But anyway, go ahead.
Okay. We're going to recall the definition of an adjoint representation. I think this was mentioned like 3 weeks ago. Okay. So recall that we can define a map called a conjugation. So that's it'll be a map from G to G that sends H to G inverse H. Sorry, GHG inverse. This is a conjugation. Notice that the derivative at identity is in the automorphism group of the Lie algebra. because this sends identity to identity. Yeah. Okay. And now we can define AD. It's from G to GLG. That sends G to this. The differential of sends G to the differential of conjugation by G at identity.
Sorry, I'm not sure what the code is. GL
of yeah. Sorry, the Lie algebra.
This is Lie algebra. Sorry, what is that?
What is the Lie algebra?
Lie algebra. What is the Lie algebra?
Yes. What is the Lie algebra?
It is a vector space equipped with a certain Lie bracket.
Okay. Yes, but in the yes, it's where does this, just as I said, and where does this vector space come from? It is the tangent space. Where at the identity of the Lie group. Yes, okay. But the first thing you said is that it's a vector space.
Yeah.
Okay, what's GL of a vector space? All invertible
matrices.
Yeah. All invertible linear transformations. Right? Baseline, G is just a vector space.
Okay. Thank you. Oh, that's right. It's the okay, makes sense.
And here I said automorphisms on the Lie algebra, but notice that how you can conjugate by the inverse. Let's say I have like this composed with conjugation by G inverse is equal to identity. So I just differentiate both sides. This is at E and this is also at E. So this is an invertible map. Okay. So because this is invertible, so I can, so the codomain can be GLG.
Yeah.
Okay. So we said that it's invertible.
Maybe don't erase the thing.
Okay, sure.
Maybe write it on the side. You have a lot of space on this side. You can have like side points on the side and then the main point. Yeah, that's right. Great.
Okay, so and there's a theorem that we want to prove, is that AD is a Lie group representation, and to prove this, we need to prove two things. One is that it's a homomorphism, group homomorphism. Okay. And we just need to check. No, this is a representation on a Lie group.
My bad, thank you.
When you have a representation on a Lie algebra, it has to preserve the Lie bracket.
Okay. This is a representation of a Lie group on the Lie algebra. Yes.
Okay.
No, everything was fine.
Oh.
I was just correcting what you said. is a representation of the Lie group. So I'm telling you how the Lie group acts on the Lie algebra.
Okay. By the way, when we say a representation here is on the board to the right, that's a representation of a Lie group, or of a group in general.
Where?
This is
the
group in
representation of any group.
Of any group.
Yeah. If it's a Lie group, then it also has to be smooth.
Yes. So it's a if G is any group, then this is just a group homomorphism. If G is a Lie group, you want this to be a Lie group homomorphism, which is just it's a smooth map.
Yeah. Okay. Let's just compute AD of GH. That's the derivative of conjugation by GH at identity, which is equal to the derivative of conjugation by G at conjugation by H applied to identity, which is equal to identity, applied to derivative of conjugation at H at identity. So this is a chain rule. And this is equal to and this is equal to add G, and this is add H. So we've proven the first point, and now we will show that it's smooth. So we want to show that.
I think. Do you not also need to show that either it sends the identity to the identity, which is obvious, or that like the inverses are the inverse is the inverse. But we already showed that. We already showed that the add of the inverse is the inverse, so it's okay. But I think that's something you would have to say.
Yeah. Yes. I think one of them is sufficient. It's either show that it's the add of inverse is inverse of add.
Yes.
Or show that identity goes to identity.
Yes.
One of them implies the other if you have this.
Yeah, that's right.
Okay.
Yeah, you're right.
We're going to, so it's sufficient to show that add of something applied to a vector v is smooth for all v in okay. And we are going to write this map as a composition of this.
This is out of something applied to v, right?
Yeah.
Yeah. Okay.
Right. We're going to write this as the composition of a bunch of smooth maps, and that will prove that it's smooth. So it is the composition of, it's okay. Map that sends G to G comma 0 E comma B. And this notation means the 0 vector at point G. So this first thing is is in the tangent space at G, and it's a 0 vector in here. Okay, so and this would be the V vector at identity. And this gets sent to so this is the vector 0, comma V at the point G, comma E. And this gets sent to the derivative of a map that I'll call C at G, E applied to 0, V. And this map C is from G cross G to G that sends GH to GHG inverse. And all of these, I think it's quite clear that these are smooth.
Okay.
And this is smooth because C is smooth, and C is smooth because, by definition, multiplication by an element is smooth.
And inverting an element is smooth.
Yes, and inverting an element is smooth. And we are going to show that this is equal to this. Okay. So add of G applied to V is equal to d dt t is equal to 0 of conjugation by G exp t v. And this is just a directional derivative. This is a path. We're just taking a derivative along this path. Okay, I should write this path. This could be any path where its derivative at 0 is V. And this is equal to C. This is by definition, and we apply the chain rule, so you have derivative of C at G, comma exp 0, and then you have d dt t equals to 0 at G, and d dt equal to 0 at exp tv. And notice that exp of 0, that's just E, so this is equal to G, comma E. This is derivative of C at G, comma E. And this is 0 because G is a constant. And this is equal to V by definition. So this is equal to derivative of C at G, comma E, applied to 0, V. So we've shown that these are the same. So this is indeed a composition of these maps, and each of those maps are smooth, so this map is smooth. Okay. Are there any questions?
Pattern matching. My brain is not so rough for this. In the bottom, are we not missing like a C?
It's here.
Oh, thank you. I thought it was a okay.
Okay.
Yeah, this whole thing, all it's saying is if I have a representation, sorry, if I have a Lie algebra and I look at the conjugation operation and take the derivative, then the derivative itself is smooth. That's all it's saying. In a Lie group, the derivative of conjugation is smooth.
Yes. So this concludes our proof to this theorem. So now we know that the Adjoint map is a Lie group representation. And then now we're going to compute it for a special case, which is where the Lie group is just matrices. Linear groups. The adjoint map at Q, the Lie algebra to the Lie algebra is just you conjugate x by q, and this is matrix multiplication. The proof is this is by definition d dt at t equals to 0 of conjugation by q applied to e to the tx. Yes.
Right. Why is the price up? What does
it's supposed to it's just this apply to any path with where the derivative at 0 is x.
Yes.
And the exponential map satisfies that. And for matrices, the exponential map is just matrix exponentiation.
Yes. So you have the conjugation map H gets sent to GH. All right. Hopefully I can stitch this correctly. But right, if you want to compute this derivative, right, instead what you could do is you could find the path gamma of t such that d dt of that path is x at t equals 0. Okay? And then you could take the derivative d dt of psi applied to gamma of t. Do you agree? Because then I can just do chain rule. Do you agree? And chain rule would be d psi, right, applied to whatever d dt of gamma is. Okay, which we chose gamma to have this be x. Okay, sorry, this is like a completely obvious thing, but I just want to say this one more time, that this is what we're doing here. We're just picking a path where the derivative at time 0 is x. Okay. I'm doing precisely the thing that I said I shouldn't do, which is erase something as soon as you said it, but that's okay.
Yes. And this is just equal to q e t to the e to the tx and q inverse. And you can think of this as left multiplication by q composed with right multiplication by q inverse applied to e to the tx. And they are both linear, so when you apply chain rule to them, to this, you get itself. So so instead you get left multiplication by q composed with right multiplication by q inverse applied to derivative of this, which is x e to the tx. Sorry, it's just x because we are taking it at t equals to 0, which is just qx q inverse. Yeah. Oh, right. This is what we wanted to show, that d rho respects the Lie bracket. So now we know how to prove this because, oh, sorry, I forgot to mention one more thing. You could recall that let's define let's just define the Lie bracket. First define this like lowercase add to be the derivative of uppercase add, and this lowercase add goes from G to the endomorphisms on G. This is the induced representation of the adjoint representation. And we define the Lie bracket to be lowercase add of x applied to y, which is also equal to d dt at t is equal to 0, add of gamma of t y, where gamma prime of 0 is equal to x. Yes, and then we are just going to prove that d phi does actually respect the Lie bracket, which implies that d phi is a representation of the Lie algebra. Sorry, not phi, rho. Let's just compute d rho applied to xy. And this is equal to d dt at t equals to 0. Add exp tx applied to y. This is just by this definition. And we can put this in front because of chain rule. So dt It's because when you differentiate this, it's equal to the derivative of this applied to this, but this is linear, so the derivative is just itself. The next one. And then we applied the definition of the adjoint representation. Which is just the derivative of conjugation, sorry, not G, conjugation by exp tx, the derivative of this at identity applied to y. Yes, and then we applied the chain rule again. This is 0, but it's to this. So this is equal to the derivative of rho composed with conjugation by exp at, sorry, composed, yes, at identity applied to y. Yeah, this is this chain rule again. And notice that rho composed with conjugation by g is equal to conjugation by rho g composed with rho. And that's just because this is equal to rho of g v g inverse, and rho is a group homomorphism, so it's rho g, rho v, and rho g inverse, which is equal to conjugation by rho g applied to rho v. So we have this. So because of this, we can substitute this for so this is derivative of conjugation by rho applied to exp tx composed with rho applied to y. And this is equal to, let's apply chain rule again to this composition. And that is equal to the different derivative of at conjugation by exptx. It should be at rho of e, but then that's just e. So at identity applied to d rho at identity of y. Okay. And now we can write it in terms of add again. Yes. So this is, think about this as this applied to this thing. So that's equal to add a rho of exp tx applied to d rho at e. And if we look at the definition, you can see that this is just equal to the Lie bracket of d rho at e x and d rho at e y.
So I mean, yes. So I mean, remember that from the very beginning, we this is something that I think we didn't even necessarily need to prove, but it's good that we did it again, because remember we defined the Lie bracket to be precisely this adjoint representation. Like we defined the Lie bracket to be this from the beginning. Okay, and then we showed at the very beginning that if I have a group homomorphism, a Lie group homomorphism, then its derivative plays nicely with the Lie bracket. And you know, here we now realize that, wait a second, the Lie brackets itself is a derivative of a group homomorphism. So that group homomorphism has to preserve the Lie bracket nicely. Isn't it? Like now the Lie bracket, we realize that this is just the derivative of some representation, but the representation is a group homomorphism. But it's just that it's a really special representation, which is kind of in terms of stuff in the Lie group, right? The adjoint representation is a representation of the Lie group on its Lie algebra. So it's like really special. It has a lot of information about the Lie group. Its derivative turns out to be this Lie bracket, which is really important. And then we realize that, of course, that this representation, the derivative of this representation preserves the Lie bracket. Okay.
A lot of
So I think this we can write as some commutative diagram, whatever.
Okay. Yes.
I think this whole proof is actually the same commutative diagram. That it's like the same one.
Is it?
From that we're gonna use later with the exponential map.
Oh.
Okay, let's recall a commutative diagram that we have seen before. So let's say phi is a group homomorphism, Lie group homomorphism. Then we have this commutative diagram. So you have phi here, and this is phi lower star, which is equal to d phi at identity, and then you have the exponential map. And this commutes. Have we proven this? I don't think we have.
We haven't. I thought we have.
Have we?
Yes. I think we prove this.
Okay.
I remember talking about it. The other thing is I'm pretty sure that proving this would be essentially the calculation that you just erased, with the exception of you would just relabel things instead of the adjoint representation. You just write, some group homomorphism, and the calculation would otherwise be identical.
Okay. Sure. Right. And so if you take this to be the adjoint representation, then we have, sorry, this to be the adjoint representation, then you have the following diagram. And in terms of equation, you can write it as AD of exp x is equal to exp lower AD x. And you can rewrite the right side as exp applied to this that's by definition. And notice that this is a linear transformation. This is exp of a linear transformation, and we have shown before that this is just matrix exponential, which means that this is equal to where this denotes like this kind of nested brackets.
So, sorry, do you understand this point of this x commutator with some blank space is a linear transformation on the Lie algebra for a fixed x? Yes, like if I fix an x, right, I can look at the operation of taking the commutator of something with x.
Mhm.
And that's a linear transformation because we checked like a commutator is whatever.
Yeah.
And so then you realize, wait a second, this thing, if I like pick a basis on my Lie algebra, I can think of this as like some matrix. This x comma,
Yes,
I can think
yes.
of that as a matrix. And I'm realizing, wait a second, I'm exponentiating this matrix.
Okay.
But we know that exponentiating a matrix, that's just like literally that Taylor series. I can write it as that Taylor series.
Okay.
For matrices, we computed that that's the case. And so then I have to like apply this, the exponential of the matrix is I apply this like, take a Lie bracket with x n times.
Yeah.
Okay, but that's essentially just the nested commutator
Yeah.
with x n times.
Okay.
Yeah, and so, yes. But then how does this look like in a more conventional way that people write this? Apply this to a vector.
Apply this to it.
So what is oh wait, sorry, this is right, we're still in the realm of Lie groups, never mind. Yes. And the like key point here is to realize that ad of x is an endomorphism on the Lie algebra, so that is a matrix. So on the right hand side we can literally do matrix exponentiation.
Yes.
On the left hand side, okay, what is on the left hand side depends on depends on what the Lie group is. But
Yeah.
then for the particularly nice case, what do we have?
Well, if G is
Write
a
it out
linear
on the
group,
other board. And turn the map.
if G is a linear group, the left-hand side is just so what we just computed what add is. It's just conjugation. If it's a linear group, so add of exp x applied to y is just equal to e to the x y e to the negative x. Yes. So for matrices, this is equal to yeah. And this is called the Campbell identity.
Yeah. So if you have like some matrix Y, then if you have some matrix Y, and you want to conjugate it by some matrix e to the x and e to the minus x, then you get this, where that is that's the commutator of matrices. And we've now proved this. Well, we've proved it by just saying, it's just this is a consequence of just that commutative diagram, and this is just a constant, this is just a fact about the adjoint representation that comes from the fact that if I exponentiate first and then do the representation, that's the same thing as exponentiating the Lie algebra representation.
That's all I have.
Yeah, I think this is a good place to stop. Okay, sounds good.
Are there any questions?
I missed the question. A linear group is just a group with
yes.
like the linear here.
It is some subgroup of GLV.
Okay.
Yeah.